module completed. The third module that was design of IIR filters. Now we'll start with design of FIR filters. Design of FIR filters. Sorry, IIR filters. So last module was design of FIR filter. Now we will start designing IIR filters. So while designing IIR filters, our task is to design digital filter, but the procedure is to design analog filter and then convert it to digital. So we will start with the design of analog filters first. Just hold it, just 1 minute. Hello. So we'll start with analog filters and specifically Butterworth filter. Analog Butterworth filter. So I have given you the classifications before. We have Butterworth filter, Chebyshev type 1, type 2, and elliptical filters are there. And our focus is only on Butterworth filter. Butterworth filter matram padicham. Is it audible?
Yes.
Okay.
Sir.
Okay, so we will start with analog Butterworth low pass filter first, specifically low pass filter. So this will be the first point of discussion. The design of digital filter start with this thing. So first thing you have to design analog low pass filter. Then you have to convert the low pass filter to required filter. Okay, this is the thing you have to learn. So how to convert a low pass filter to high pass, band pass, and band stop filters, still in the analog world only. So with these two topics, you will be able to design analog Butterworth low pass filter and the remaining say high pass, band pass, and band stop filters. So with these two topics, you will be able to design analog Butterworth filter. Now the last topic is you have to convert it to digital. So you have to design digital filter. Okay, you have to design digital filter. So designing digital filter means we have already designed analog filter. Now you have to convert it to digital. Okay, so what we are doing here will be you have to convert analog filter to digital. You have to convert analog. Already you have designed analog filter. Then you will convert it to digital. And this can be done in two ways, or we have two methods to do that. First method is called impulse invariance method. Okay, impulse invariance method. And second one is called bilinear transformation. Bilinear transformation. Got it. So this will be the end of module 4. So this is design of IIR filters. We will start. So if you want to design an IIR filter, first you have to design analog filter, then convert it to digital. So first half section, we will discuss about the design of analog filters itself. And I will give you this classification. Clear the classifications. IIR filters, you have Butterworth filter. Okay. You have Butterworth filter. Then you have Chebyshev filter. Chebyshev filter itself, you have type 1 and type 2 filters. And another type is elliptical filter. Elliptical filter. So these are different types of IIR filters. And your focus will be only on Butterworth filter. Clear? I have IIR filter design. There are Butterworth, Chebyshev, and elliptical filters. For your syllabus, you have to discuss only Butterworth filter. So we will start with the analog Butterworth low pass filter. Then we will convert it to your required specification, maybe high pass, band pass, or bands. So even though if you want to design a high pass filter, first you have to design low pass, then you will convert it to low pass. So that is the relevance of the second heading: low pass to required filter conversion. Okay, low pass to required filter conversion. Then after completing analog filter, you will convert it to digital using two methods: impulse invariance and bilinear transformation. This is a simple method, and this one is a bit complicated and very important. Bilinear transformation. Clarity else we will start with filter design. Today I will give you some theory parts and we'll start doing problems from the next class. Can I start?
Yes, sir.
Okay, so we will start. What should be the first topic? First heading? Design
Analog butterworth.
Definitely you have to start. That's fundamental. You have to start designing an analog butterworth low pass filter, right? So you can make a heading analog butterworth low pass filter. Analog butterworth low pass filter. Analog butterworth low pass filter. So let me introduce you some terms before starting this. Let me draw a frequency response of a low pass filter. Lab design but now this is my frequency axis, capital omega. Okay, I am not using small omega over here. Instead, I use capital omega. You should be able to distinguish between capital omega and small omega. This is small letter omega, and this is capital omega. Okay, so what is the difference between these two people? Both are frequencies. What is the difference between capital omega and small omega when you represent it for a particular frequency? Frequency not in the small omega is for digital frequency and capital omega is for analog frequency. Okay, capital omega means like you're dealing with an analog frequency. So that means you're designing this is a frequency response of an analog filter. Okay, filter analog that's it. That's more clear. It's an analog frequency response. So let me draw a low pass filter response. Low pass filter see it comes like this. Transition band, and here you have the stop band, right? So if you're expressing it in dB, what should be this value? Pattern. This is pass band. This is stop band.
1 dB.
dB.
0 dB.
0 dB. 1 is the gain. Okay. P out by V means 1. 20 log 1, that will be 0. So this is 0 dB. And actually your pass band ends here. Then decrease is okay, but you are ready to accept some part of attenuation or some kind of attenuation. And you call it as tolerance. That was the tolerance in pass band. So what was the notation that we used in your lab classes? RP okay. So you can call it as delta P RP delta type MATLAB R use. Okay, so you can call it as alpha P, delta or alpha P. Okay, so this is pass band tolerance. So what will be this point? Can you name it?
FP, pass band frequency.
Pass band edge frequency, right? FP, and this is omega axis, so it will be omega P. Okay, right? Similarly, in stop band also, I'm going to give a tolerance level. This is a stop band and expecting I'm going to give a tolerance level like this. And that can be called as alpha S. And this is my omega S, stop band edge frequency. But FP, FSL use the omega L, that's why I'm using the symbol omega P and omega S. If it was F, you can use FP and FS, no issues. Are you clear with all these terms? Alpha S has to be measured from this line, right? This is alpha S. This is alpha S. So this is the case if you express everything in dB. The dB will express in the case, right? Isn't it? So instead of dB, this can be in gain also. Gain the formula. In terms of gain, what will be this value? This is 1. Like 0 dB is actually 1. The gain is 1. Similarly, alpha P. At this particular point, the gain will be 1 by root of 1 plus epsilon square. There is a term called epsilon. So this is referred as 1 by root of 1 by epsilon square. So then a dB will express is alpha P. So you can write it like this also. Alpha P. What is your alpha P? That is 1 by root of 1 plus epsilon square expressed in dB. This dB will express similarly alpha S. Alpha S that is actually a parameter in dB. Here you have another term called 1 by root of 1 plus lambda square. 1 by root of 1 plus lambda square. So we can say like this. Alpha S is actually 1 by root of 1 plus lambda square expressed in dB. This dB will express in the value on alpha S. In gain format, you can say that it is 1 by root of 1 plus lambda square. ഇത്രയും കാര്യങ്ങളൊന്ന് നോട്ട് ചെയ്തോളൂ. നമ്മൾ പുതിയ 1-2 ടേംസ് പഠിച്ചു. എപ്സിലോൺ ആൻഡ് ലാംഡ. ഓക്കെ, എപ്സിലോൺ ആൻഡ് ലാംഡ. സോ ആൽഫ പി എന്താണ് നമ്മൾ പറഞ്ഞത്? Can you give me an equation for alpha P? Express this in dB. So what will be that? 20 log 1 by root of 1 plus epsilon square. So that is actually alpha P. So my concern is not alpha P. I want an equation for epsilon. Can you rearrange it and find a value for epsilon? This is logarithm to the base 10, right? Just try to rearrange and get me an equation for epsilon. You can write alpha P is equal to 20 log 1. Log A by B is log A minus log B. So 20 log 1. Sorry, this is 20. 20 log 1 minus 20 log root of 1 plus epsilon square. Log 1 is 0. So this term will become 0. Which implies alpha P equal to minus 20 log 1 plus epsilon square, right? Log 1 plus epsilon square root in you can write it like this, raised to 1 by 2. Isn't it? So raised to 1 by 2 cancel here. So that is equal to minus 20 by 2. That will become 10 log 1 plus epsilon square. Which implies okay, logarithm base is 10. This can rearrange here. So alpha P by 10, 0.1 alpha P. 0.1 alpha P equal to minus log 1 plus epsilon square. This chain on the Kanichan, direct equation. Okay. Minus logarithm base is 10. Now log ഒഴിവാക്കാം വേണ്ടി എന്ത് ചെയ്യാം? ഈ മൈനസ് ഞാൻ ഇപ്പുറത്തിടാം. Log ഒഴിവാക്കാൻ വേണ്ടി എന്ത് ചെയ്യാം? You have to take 10 raised to. So which implies take 10 raised to on both sides. 10 raised to minus 0.1 alpha P is equal to log and 10 raised to will cancel. So this will be 1 plus epsilon square, which implies epsilon is equal to minus 1 ഇപ്പുറത്തേക്ക് എടുക്കുക. 10 raised to minus 0.1 എന്ന് പറയുമ്പോൾ 1 by 10 raised to എന്ന് പറഞ്ഞാൽ എഴുതാം അല്ലേ? Okay, so epsilon is equal to, sorry, mistake ഉണ്ടല്ലോ. Actually, minus sign would disappear because alpha P is negative. Log 1 minus alpha P value, it's actually negative value. So you can keep minus alpha P keep here. So minus will become plus. So what will be epsilon from this? minus 1 ഈ സൈഡിലേക്ക് എടുക്കുക, റൂട്ട് എടുക്കുക. 10 raised to 0.1 alpha p minus 1. So that will be the equation for epsilon. Similarly, lambda is equal to root of 10 raised to 0.1 alpha s minus 1. What do you tell? Just note these equations. Epsilon is 10 raised to 0.1 alpha p minus 1 and lambda is 10 raised to 0.1 alpha s minus 1. I will make the thing more clear. See, if the value of alpha p is given us, passband edge is given us minus 3 dB or minus 2 dB. നിങ്ങൾ ഇതിന്റെ നെഗറ്റീവ് സൈൻ ഈ ഇക്വേഷൻ കൺസിഡർ ചെയ്യണോ? alpha p minus 2 dB, 2 dB എന്നൊക്കെ സാധാരണ പറയാറുള്ളൂ. ഇൻ കേസ് minus 2 ഗ്രാഫിക്കൽ ആയിട്ട് വരികയാണെന്ന് വിചാരിക്കാം. This is minus 2. So should I substitute it as minus 2 or plus 2? Plus 2 ആയിട്ട് തന്നെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്താൽ മതി, ബിക്കോസ് ഇവിടെ നമ്മൾ ആ മൈനസ് സൈൻ ഓൾറെഡി അക്കൗണ്ട് ചെയ്ത് കഴിഞ്ഞു. ഓക്കെ, സോ യു ക്യാൻ സബ്സ്റ്റിറ്റ്യൂട്ട് ആൽഫ പി എസ് ജസ്റ്റ് പ്ലസ് 2 dB ഡയറക്റ്റ് പോസിറ്റീവ് ആയിട്ടുള്ള വാല്യൂ ഇവിടെ യൂസ് ചെയ്താൽ മതി. So this is the equation for epsilon and lambda. ആർക്കെങ്കിലും ക്ലാരിറ്റി വേണമെങ്കിൽ ചോദിക്കാം.
സർ, alpha p is equal to 1/1 plus epsilon naught in dB ഒന്നില്ലേ? അപ്പോ അത് alpha p is equal to 1/1 by SL under root 1 by epsilon naught. അത് ഇവിടെ നമ്മുടെ ഇക്വേഷൻ.
ഇതോ ഇത് എപ്സിലോൺ എന്ന് പറയുന്ന ഒരു ടേമിനെ അവിടെ അങ്ങനെ എക്സ്പ്രസ് ചെയ്തതാണ്. നമുക്ക് അത് ആക്ച്വലി ഇങ്ങനൊരു എപ്സിലോൺ എന്ന് പറയുന്ന ഒരു ടേം വേണം നമ്മുടെ ഇക്വേഷൻസിനെ സിംപ്ലിഫൈ ചെയ്യാൻ വേണ്ടിയാണ്. അല്ലെങ്കിൽ ഡിസൈൻ സ്റ്റെപ്പ് വരുമ്പോൾ മനസ്സിലാവും ഇക്വേഷൻ കുറച്ച് കോംപ്ലിക്കേറ്റഡ് ആവും. ഇക്വേഷൻ സിംപ്ലിഫൈ ചെയ്യാൻ വേണ്ടി മാത്തമാറ്റിക്കലി ഇതിനെ ഇങ്ങനെ മോഡൽ ചെയ്തു എന്നുള്ളതേ ഉള്ളൂ. നമ്മളിനി ഒരു ഓർഡർ കണ്ടുപിടിക്കുന്ന ഇക്വേഷൻ ഒക്കെ ഉണ്ട്. അപ്പൊ അവിടെ ലോഗ് ലാംഡ ബൈ എപ്സിലോൺ എന്നാണ് ന്യൂമറേറ്റർ വരുന്നത്. അപ്പൊ നമുക്ക് പഠിക്കാൻ എളുപ്പം അതാണ്. അല്ലെങ്കിൽ നിങ്ങൾ എന്ത് ചെയ്യണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ ലോഗ് ഒരു കോംപ്ലിക്കേറ്റഡ് ടേം വരുവാണ്. ഇതിനെ സിംപ്ലിഫൈ ചെയ്യാൻ വേണ്ടി ആൽഫ ബൈ എപ്സിലോൺ എന്ന് ആക്കിയതാണ്. യു ലുക്ക് ഇൻ ടു ദാറ്റ്. ഡിസൈൻ സ്റ്റെപ്പ് നോക്കുമ്പോൾ മനസ്സിലാവും. സോ ഇത്തരം കാര്യങ്ങൾ ക്ലിയർ ആയിരിക്കണം. വി വിൽ സ്റ്റാർട്ട് ദ ഡിസൈൻ പ്രൊസീജിയർ. ഡിസൈൻ പ്രൊസീജിയർ ഒന്ന് നോട്ട് ചെയ്യാം. സോ you should be very comfortable with alpha p and alpha s. These are the values in dB. Okay, and 1 by root of 1 plus epsilon square and 1 by root of 1 plus lambda square. This is the normal values. Okay, then a dB will convert to alpha p. So even though when alpha p is given and alpha s is given, you have to find epsilon and lambda. So that can be done with the help of these two equations. Just by heart these equations. Lambda is equal to 10 raised to 0.1 alpha s minus 1 and epsilon is 10 raised to 0.1 alpha p minus 1. You make the next heading. നമുക്ക് ഇത് വീണ്ടും ഒന്നുകൂടെ വേണം നോക്കാം. Next heading, design procedure. Design procedure. Design procedure. So first step, from the given specification, find order of the filter from the given specification. Given specification means this alpha p, alpha s, omega p and omega s will be given to you as we have done in MATLAB. MATLAB will be these specifications will be given to you. So first step is you have to compute the order of the filter that is given by the equation. In MATLAB you use the command buttord, buttord. Buttord command was used to calculate the order and cutoff frequency, isn't it? So here also you have to find the order. We will do that mathematically. So to find the order, this is the equation. So the equation is given like this. Order is greater than or equal to. That means order will be a real number only, right? So you have to round off these decimals. We'll see that. So the equation is n greater than or equal to log lambda by epsilon. This is the numerator. Divided by log omega s divided by omega p. So this is the equation to find the order of a Butterworth low pass filter. See, the equation is very simple, lambda by epsilon in terms of lambda. Else, that will be complicated. Root of 10 raised to 0.1 alpha p. You have to express in terms of alpha p and alpha s. So, that's simplify lambda epsilon. Here, mathematical modeling use. Clear, right? This is the equation for order. So, that is the first step. You have to calculate the order. So, for example, if the order is 3.2, you are getting the order as 3.2. Okay, you have said, or 3.1, you have to round it to 4. Next higher value like round it. Even though it is 3.5 or 3.1, even though if it is less than 3.1, you have to round it to the next higher value, that is 4. Clear? So this is how you can compute the order. Second step, you have to draw a table. Second step is choose h of s. Choose h of s according to the order. Choose h of s according to the order. I have written h of s because you are designing analog transfer function. Okay, so your h of s will be depending upon the order, you have to choose the h of s value. Let's formulate a table. Say this is the order, and here you will have the denominator of h of s. Denominator of h of s. The numerator will be 1. h of s in the numerator 1 ആയിരിക്കും. We will see what will be the denominator. അല്ലെങ്കിൽ ഇവിടെ എപ്പോഴും 1 by 1 by എന്ന് പറഞ്ഞ് ഇത് ഫോർമുലേറ്റ് ചെയ്യണം. ഒരു എളുപ്പത്തിന് വേണ്ടി ഞാൻ denominator of h of s എഴുതുക. So if the order is 1, the denominator is s plus 1. That means your h of s is 1 by s plus 1. Transfer function is for the first order. Got it? If the order is 2, you have to by heart this table for at least order 5. Okay. Or maximum up to 4. Will exam choice chance. For second order Butterworth filter, the numerator is 1. The numerator is always 1, and the denominator will be s square plus root 2s plus 1. For third order, you just copy this table for the time being. This will be s plus 1 into s square plus s plus 1. So for a third order Butterworth low pass filter, h of s will be 1 by s plus 1 into s square plus s plus 1. Got it? This is the denominator. Now the fourth, if the order is 4, this will be s square plus 0.76 537 s plus 1 into order will be 4. Again, you will have a second order polynomial s square plus 1.877 s plus 1. And if the order is 5, s plus 1 into s square plus 0.61803. You can see this table in your textbooks, into s square plus 1.61803 s plus 1. 5 is enough. You can refer your textbooks for the transfer function for order 6 and 7 also. Okay, for the time being you stop with 5. So this is the second step. First you have to calculate the order, and the second step is from the given order you have to choose one transfer function. You have to fix your transfer function. You make a note over there, very important. You make a note over there. The above table is created for omega c is equal to 1 radian per second. Okay, it's created for 1 radian per second. That means for this transfer function, for say for if your order is 1, this will be a transfer function. Your cutoff frequency will be 1. Your cutoff frequency will be 1. Now you have to change the cutoff frequency to your required cutoff frequency. Our expected cutoff frequency is not what, that will be something different. So you will have, say, the cutoff frequency 3 dB line. If I draw the 3 dB line minus 3 dB line, so that comes somewhere over here. So this is my cutoff frequency, omega c. Your omega c will be something different. The above filter will have a cutoff frequency of 1 radiance filter. So the third step will be transform your cutoff frequency, or you have to calculate your cutoff frequency. This is the third step. Calculate our omega c. Calculate our omega c. You have to calculate our cutoff frequency. For that, you can use this equation. Omega c is equal to omega p by epsilon raised to 1 by n. Or there are two options. This is a design giving importance to pass band. Pass band in a stress is on design. We'll see the difference. And if you want to give importance to stop band, then you can use this equation, lambda raised to 1 by n. So this is omega c equal to omega p by epsilon raised to 1 by n, or omega c equal to omega s by lambda raised to 1 by n. You can use any of these equations. The problem is so talkalam steps note here. And the last step is, so by this thing you will be so the last step is you are designing low pass filter, right? So you have to do the frequency transformation. Last step is do frequency transformation. Frequency transformation. That means here you will have a S term, right? H of s into other S on H of s is 1 by s plus 1. Okay. So that S has to be replaced now. S in replace here. So low pass filter design S has to be replaced with S by omega c. So this will be the last step. S in S by omega c design substitute here, so that you will complete the design of a low pass filter. First you have to calculate the order. You have to calculate your order. First you have to calculate your order. Second thing, you have to choose denominator for your transfer function. Numerator is 1. You have to choose the denominator according to the order from this. H of s this will be a Butterworth low pass filter. Okay. So the cutoff frequency that will be 1. 1 where in the table formulate. Now you have to shift, you have to convert this design to your design. Number design you need some other cutoff frequency. Something like this. Near cutoff frequency you will have some values. So you have to calculate the cutoff frequency for your particular criteria. Given omega p, omega s from alpha p and alpha s, you can calculate this epsilon and lambda values. So you have to identify your cutoff frequency. Now you have to transform this thing, this design, according to the given specification. In the given specification and cutoff frequency. So you have to do the transformation. You have to change it from 1. 1 will cutoff frequency transform. To do that, you have to substitute, replace S with S by omega c. So with this step, you will be done with a Butterworth low pass filter design. So we have a problem with these steps. We will clarity. The steps copy. I will give you 1 minute. Clarity.
Sir, order equation. Okay, sir. Okay, sir.
വേറെ എന്തെങ്കിലും ക്ലാരിറ്റി വേണോ? ഇതെല്ലാം കോപ്പി ചെയ്ത് കഴിഞ്ഞോ? നമുക്ക് ഇന്ന് ഒരു ഫിൽട്ടർ ഡിസൈൻ അടുത്ത ദിവസം ചെയ്യും. എനിക്ക് സമയമില്ല. ജസ്റ്റ് ഒരു ഷോർട്ട് പ്രോബ്ലം ഒന്ന് ചെയ്ത് നോക്കാം. ചുമ്മാ ടേംസ് ഒക്കെ ഒന്ന് ഫെമിലിയർ ആവാൻ വേണ്ടി. ഓക്കെ, നമുക്ക് ജസ്റ്റ് ഓർഡർ മാത്രം ഒന്ന് കമ്പ്യൂട്ട് ചെയ്ത് നിർത്താം. റൈറ്റ് വൺ ക്വസ്റ്റ്യൻ. ഇനി ടൈം വേണം ഇത് കോപ്പി ചെയ്യാൻ. എനിവൺ? First step is calculating order. Second step, you have to choose one transfer function. Third step, you have to calculate cutoff frequency. Last step, you have to convert your transfer function for the calculated cutoff frequency. So that can be done like this. This can be replaced with S by omega C, so that you will get a low-pass filter. So write first question. For the given specification, determine the order of IIR Butterworth filter. For the given specification, determine the order of IIR Butterworth filter. Alpha P is 1 dB. Alpha P is 1 dB. These are the specifications. Alpha P is 1 dB. Just order matram compute ചെയ്താൽ മതി. Alpha S is 30 dB. Alpha S is 30 dB. That is stop band attenuation, stop band tolerance. Then omega P is 200 radians per second, and omega S equal to 600 radians per second. So ഒരു പ്ലെയിൻ ക്വസ്റ്റൻ ആണ്. ജസ്റ്റ് ഓർഡർ കാൽക്കുലേറ്റ് ചെയ്യാം. ഇക്വേഷൻ ഒന്ന് കംഫർട്ടബിൾ ആവും. ദാറ്റ്സ് ഒരു റെസ്പോൺസും വേണം. ചുമ്മാ ഒന്ന് വരച്ചു നോക്കും. All of you just draw this response also. റെസ്പോൺസ് വരച്ച് അതിൽ ഈ വാല്യൂസ് ഒക്കെ ഒന്ന് മാർക്ക് ചെയ്യാം. അപ്പം കുറച്ചുകൂടെ ഐഡിയ ക്ലിയർ ആവും. ലോ പാസ് ഫിൽട്ടർ ആണ്. ആക്സിസ് എപ്പോഴും മാർക്ക് ചെയ്യുക. ഇറ്റ്സ് ക്യാപിറ്റൽ ഒമേഗ. ബൈ ക്യാപിറ്റൽ ഒമേഗ
അനലോഗ്
ആണ്. ഓക്കെ, ഇറ്റ്സ് അനലോഗ് ഫിൽട്ടർ. സോ പാസ് ബാൻഡ് ലോ പാസ് ഫിൽട്ടർ ആണ് അല്ലേ? ഇപ്പൊ ലോ പാസ് ഫിൽറ്ററിന്റെ ഷേപ്പിൽ വരയ്ക്കുക റെസ്പോൺസ്. ലോ പാസ് ഫിൽട്ടർ ആണ്. പാസ് ബാൻഡ് എഡ്ജ് 200 ഹെർട്സ്. സോ സംവെയർ ഓവർ ഹിയർ 200 റേഡിയൻസ് പെർ സെക്കൻഡ്. ഒമേഗയിലാണ് 2π. സോ 200ന്റെ ലെവലിൽ വരേണ്ട വാല്യൂ എന്താണ്? ഇവിടെ വരേണ്ട 1 dB. So this is 0 dB and this is 1 dB. -1 ആയിരിക്കും. Then 600 radians per second. That is your omega S stop band edge. This is pass band edge. And there that should be 30 dB. Like stop band edge. ഇത് 30 dB മെഷർ ചെയ്യുന്ന എപ്പോഴും ഇവിടെ നിന്നാണ്. 0-ൽ നിന്നാണ് താഴേക്കാണ് മെഷർ ചെയ്യുന്നത്. ദാറ്റ് ഈസ് യുവർ ആൽഫ എസ്. ഈ പ്രോബ്ലം ചെയ്യാൻ ഇതിന്റെ ആവശ്യമില്ല. ജസ്റ്റ് ഐഡിയ കിട്ടാൻ വേണ്ടി പറഞ്ഞതേ ഉള്ളൂ. യു ക്യാൻ ഡയറക്ട്ലി യൂസ് ദ ഇക്വേഷൻസ്. വാട്ട് ഈസ് ഇക്വേഷൻ ഫോർ ഓർഡർ? ലോഗ് ലാംഡ ബൈ എപ്സിലോൺ ഡിവൈഡഡ് ബൈ ലോഗ് ഒമേഗ എസ് ബൈ ഒമേഗ പി. അല്ലേ? ഒമേഗ എസ് ബൈ ഒമേഗ. സോ ഫൈൻഡ് ദ വാല്യൂ ഓഫ് ലാംഡ ആൻഡ് എപ്സിലോൺ. ലാംഡ എപ്സിലോൺ കണ്ടുപിടിക്കണം. ഫൈൻഡ് ദ വാല്യൂ ഓഫ് ലാംഡ 10 raised to 0.1. ലാംഡ എന്ന് പറയുന്നത് സ്റ്റോപ്പ് ബാൻഡിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ളതാണ് അല്ലേ? So alpha S -1. Similarly, find epsilon also and tell me the values. Epsilon de lambda de values in the പറയാം. Just do that. അതിന്റെ പേര്. കിട്ടിയ വാല്യൂ എന്ന് പറയും ലാംഡയുടെ എന്തെങ്കിലും ആൻസർ ഇല്ല. ഓർഡർ 4 ആണ് വരുന്നത്. 3.758 വരും എന്നിന്റെ വാല്യൂ. 3.75 കണ്ടു വരും. ആണോ? ചെക്ക് ചെയ്ത് നോക്കിയാൽ ലാംഡയുടെ വാല്യൂ എത്ര വരും? 31.6. എപ്സിലോൺ 0.508. Then substitute the values and find. ആണോ? 3 പോയിന്റ് ആണോ വരുന്നത്?
3.75.
Okay, 3.75 is the value. So you have to choose a value greater than that. Therefore, order is 4. So actually, in procedure, h of s value in the you have to choose from the table. Then you have to find cutoff frequency. And then procedure. Okay.